Okay, folks, welcome back, everyone. Hello, greetings. Happy to see you all. So I want to come back to an example that we were looking at on the end of Thursday there. So at the end of Tuesday night, rather, we are trying to do the following thing. So we were doing a little bit of optimization, and our goal was the following. Okay, we wanted to maximize a given function, which was the following guy. Okay, maximize this function on the sphere x squared, y squared, z squared is 9. Okay, so we wanted to maximize that function on the sphere of radius 3. And I was illustrating what was going on with that in class Tuesday night. I want to take you through that illustration again because it has sort of the key idea for today's lecture. Okay, it's got most of the idea for today. Is the mic okay? We're good? All right. So the key idea here is to think of level curves of this function. Okay, so we're going to pay attention to level curves of this guy. Okay, so level curves, we've seen them before when doing contour plots. Now we're doing them in 3D. Right, so we find all the solutions to this. We're going to look at the level curves of this guy and see where they meet that sphere. Okay, so let's see how that looks visually. So here I've got the level curve, that's this blue plane. The level curve 7, right? So that's this guy. And then I've got my sphere here. And watch what happens as we increase the value of k. Right? So as we increase the value of k, we go from 7 to 9, and the plane shifts down a little bit. Right, so as we go from 7 to 9, this plane switches to the plane below it. As we go from 9 to 11, we'll see this plane shift again. Right? We see that it shifts down to that guy. Okay, so what we're seeing is we're seeing these planes move through space in a particular direction. Okay, so sort of schematically, here's our red sphere. And then we've got planes cutting like this now. And as we increase k, they're headed this way. Okay, so let's keep moving them. To go from 11 to 13, we shift a little bit to this new plane. And now we've moved down even a little bit further. So our goal is to find the largest value of k so that this plane still touches the region. Right? So if we maybe put in 20, it still touches the region. 25, we can see there's a little bit of touching still happening there. 26. 27, and now we're no longer touching the region. Okay, so what that's telling us is that our maximum is somewhere between k equals 26 and k equals 27. So let's see, 26 is there. 26.5, is that still touching? No, that's no longer touching. Okay, so our idea for today is that when that maximum occurs, our level sets should be tangent to the constraint. Okay, so the maximum, wherever it lives, should be here, and it should be tangent to the constraint, right? Because before it leaves the surface, it has to touch the surface at one point. Okay, so let's just make a note of that. Okay, are there questions there or thoughts there? I encourage you to play around with GeoGebra a little bit. There's a link to it in our syllabus, and if you pull up GeoGebra, you can kind of like move this constraint around yourself, etc. Okay, so I think we're done with the computer for now. Let's do the rest on the board. Oh. Great. Okay, so let's find formally where that tangency occurs. Right? We know it's somewhere between 26 and 26 and a half, I think. So let's find where this blue dot actually is. Yeah? Notice all of those planes that we've got are parallel, and they all have the same normal. So let's finish off this example. So we'll put a little comment that we're going to find the point of tangency. All of these planes have the same normal which we can get by reading off the coefficient of x, y, z here. Like this. So now we're going to find where that normal line meets the sphere. So in our diagram, right, that normal line will meet the sphere at two spots, and we'll find where that spot is there. Okay, so we want to find where the line given by that normal meets the sphere. So to do that, we'll plug in the equation of that line into the equation of the sphere. And now this is the kind of thing we can solve for t. So what do we get? We get 29. T squared is 9. Okay, so we get two solutions. Those are the 2 points of intersection, right? The top one and the bottom one. We want to make this function as large as possible. So we want to plug in negative numbers for x, y, and z. If we plug in negative numbers, they'll cancel the negatives we have, and we'll get a large positive value. Right, so plugging these guys in here, we'll get some large value for our function. Okay, are there any questions there, thoughts there about how that calculation goes? Right, what's the negative root correspond to? Right, so if we put t is equal to the negative root, what would we get then? Yeah? Yeah, so right, so if we dialed back that k, if we move backwards, we're going to get smaller and smaller values of our function. So the other direction for t will give us the minimum here. Okay. Very good. All right, so I'd like to do another example of this kind of thinking. Okay, this idea of using a point of tangency to find an optimum. Okay, questions there before we move on? Okay, so let's do another one where the level curves are a bit more complicated now. Okay, so let's follow through with this idea of using tangency to find the max. So what's this function look like? What does this set look like? Okay, so here our constraint is a circle again. So there's our circle of radius 1. And now the level sets of f, they're going to be hyperbolas. Right? So we're going to say the product of x and y should be equal to 1, say. Okay, so this will be is that right? Maybe it's smaller value. No. Okay, so let's say that's one of these sort of small level sets. Then we get another level set like this. Ninth. Okay, and we can see that as we increase this value of k, these level sets are going to move out and out. Right? They're going to get closer and closer to being tangent to our circle. Okay, so we've drawn the constraint. Which is this guy. We draw some level sets. Okay, but now we're in this funny position. How do we find the point of tangency here? Right? What condition will give us that these guys are tangent? Well, they certainly need to be solved at the same time. Right? We need a solution of the blue curves that lives on the red curve. Right? But it's hard to solve these two guys at the same time. Like we can't, plug in this guy here or vice versa or anything. So I propose that we do the following. Okay, so observe that these guys have a line of symmetry here. Right? They're both symmetric about y equals x. So we can flip this whole picture about that line. The red curve maps to itself. The blue curve maps to itself. So now we want to find a point of tangency on that line. So we're going to assume that the point of tangency happens somewhere along this line, right? As we move the blue curves, they're going to intersect with that line, and we're going to move them until they touch just at that one red point. And now we can solve for the x coordinates here. Okay, so there's a solution for x. Okay. So we get that they touch at exactly one point there. At this guy and this guy, the two curves meet. So we get 2 points where the curves are touching at exactly one spot. Okay. And when we plug in those values, we get, large values for this function. And these guys seem to be a maxima. Which is good because we were looking for the maxima. But this doesn't give us any insight into how to find the minima for this function. Right? It's not clear how to get, from what we've written down so far, how to get the mins. Okay? There's one observation I want to make here about this point of tangency. Okay, so I want to look at the gradient at that point of tangency. Okay, so what do we get there? The gradient will be this guy. Okay, and our constraint is this guy here. Okay, so these functions look quite different, but I want to observe what happens at the points of intersection. Okay, so at the point of intersection, the gradients are parallel. What does that tell us about the tangent planes? What does it say about the tangent plane to this function and the tangent plane to this function? Okay, one sec. Maybe another end, someone else in the audience. Yeah, over here? Yeah, that means that they have the same tangent plane. So the gradient vector is normal to the tangent plane. So if these guys have parallel gradients, then they have the same normal for their tangent plane. They touch at one point, same normal of tangent plane, so same tangent plane. Okay, so they're parallel, and that tells us that they have the same tangent thing. Okay, so so here we had to use this kind of like, this sort of symmetry argument. But I think that this is the way to go. If we're looking for points of tangency, I think that we want to be looking at gradient vectors. Okay, so I want to build this into a method for optimizing now. Okay, so now we're going to introduce this thing called the method of Lagrange multipliers, and what it does is it makes this into a method for finding these optima. Okay, so what does it say? Okay, to optimize a function subject to a particular constraint, we're going to define the following weird function. So this is a fancy letter L. Okay, if you want to follow along with that same fancy L, you go up, make a curl, down, make a curl, like that. Right? Very lovely letter. It's right up there with like infinity in terms of my favorite things to draw. Okay. So up, down, like that. Okay. So that's L for Lagrange. And we're going to define our function like this. So it's going to take the same input, and it's going to take an extra lambda. And we'll say what that lambda does in a minute. Okay. From time to time, people ask if they can put a plus sign here. I would strongly prefer if you put a minus sign here. Okay, if you learn this in another course, that's fine, I understand. Please put a minus sign there. Okay, so you define this function. Find the critical points of L. And then you select those critical points that minimize or maximize f. Okay, so let's see how this comes back to parallel gradients, because right now it doesn't really look like the gradient's involved at all. So there's a couple observations I want to make. The first is to get these gradients back. So if we're taking the derivative of this guy in terms of x, we're going to get the derivatives in terms of x of the other guys. And we take the derivatives, and then this is set to be equal to 0. Right? So our critical point means our derivative in x is 0. Right? Now we take our derivatives in y. And equivalent to this is the following notion. We can say that bringing the lambda stuff over to the other side right? We've got this. But these guys are the components of the gradient vector. Right? So this is the x component of the gradient. This is the y component of the gradient. So what we wind up getting is that here's the components of the f gradient. And there's the components of the g gradient. Okay, so really what this, what being a critical point is all about is that we get parallel gradients. Okay, so that's observation 1, is that these guys wind up having parallel gradients. Observation 2, okay, observation 2 is that when we say that the derivative of this guy with respect to lambda is 0, right? When we take the derivative of this Lagrange function with respect to lambda, we get the following thing, right? There's no lambdas in here, so that all goes to 0. There's no lambdas in here, so the only lambda we care about is this one. So that tells us negative g of x is 0. Or g of x is 0. Okay, so that's why we set up our constraint so that it equals out to 0 here. Okay, the satisfying that constraint is built into the system. Okay, so if we are a critical point of the Lagrange function, then the gradients are parallel and we satisfy the given constraint. Okay? So if I could go back and rename this, I wouldn't call this Lagrange multipliers because it's very mysterious. I would call this the method of parallel gradients. Okay? Because that's the key idea, that the optimal value should be tangent to the constraint. Okay, so that's the theory of the thing. Are there any questions about the theory? Yeah, sure.
So when we find a partial derivatives, it's for all the components of the vector x and lambda.
Yes. Yeah. When it says critical points here, this is with respect to x and lambda. Yeah, over here. Is it guaranteed? Let's see. Probably not. There's probably something tricky that goes wrong. All of the examples we'll do will have at least one critical point, though. Okay? Yeah. Yes, it is an application of that. So last class we talked about the extreme value theorem, and that told us on compact bounded things we always have extreme value, right? So as long as our constraint is compact, right? So as long as our constraint is like a ball or like something that's bounded and closed, then we'll have a critical point and we'll have an extreme value. Something tricky could go wrong if this was like a plane, but let's not dwell on that. All our constraints will be compact. Okay, other questions or thoughts there? So now I want to go back and look at that same example with the hyperbolas and the circle, but I want to do it through this lens. So when we did x, y on the circle, we got a we got a max, but we didn't really know why. And now I want to be able to find the maxes and the mins at the same time. Okay, so let's redo this through the technique of Lagrange multipliers. Okay, so looking at this, we want to optimize f subject to a constraint that equals 0. Right now, though, we've got a constraint that equals 1. So we have to start off by rewriting the constraint. Okay, so that we get something that equals 0. So we bring that 1 over to the other side. Okay, now we set up the Lagrange function. All right, so we plug it in exactly for that L. Okay, now we go ahead with the critical points. Okay, to save a little bit of writing, I'm going to write this derivative as L sub x. Okay, and then so that's the derivative in terms of x. So that will be y minus lambda 2x 0. All right, and then this last one, we just get our constraint back. Okay, so there are our conditions for being a critical point. One of the things that makes this method a little tricky is that the equations you get are often nonlinear. So it's often a little bit tricky to find the critical point given this setup. Okay, so let's rewrite these in a way that might make them easier to solve. Okay, I'm going to bring this stuff involving lambda over to the other side. Okay, now I get here. Any suggestions on how I can start solving these guys? There's a bit of a knack to solving these things, so I recommend trying out, a move or two to try and solve these. Okay, so maybe take, I don't know, let's say 2 minutes and try and solve those. Okay, simultaneously. Okay, yeah, good. Okay, yeah, so good. Were people able to make some progress on that? Yeah? Okay, sweet. So the idea here, there's several different ways to approach this. Okay, so let's go with one method of solving for, let's say, for x. Okay, let's solve for x first and see what we can get. So one particular method of approach would be to say x is 2 lambda times y, but y is 2 lambda times x. Now we've got an equation that just involves x. Okay. So we need to be a little bit careful about dividing out that x. Why do we need to be so careful? Yeah?
X could be 0.
Yeah, if x is 0, then we can't divide out both sides here. Okay, so either x is 0 or 1 is 4 lambda squared. Okay, if x is 0, right? X is 0, well, that tells us immediately that y is 0. Okay, but if y is 0, both of these guys are 0, they can't square and add up to 1. Okay, so okay, so this is bad. That point is not on the circle. That's a sad thing. Or another way of saying that, that's a contradiction. Okay, so let's work with the this side of the equation. Okay, that tells us lambda is plus or minus a half. So going this way, we can split into two cases. We can split into the case where we're negative a half. Okay, and now we see that there's two possibilities. What I like about this Lagrange multipliers approach is that symmetry y equals x just comes out naturally from the setup. We don't have to notice it. We don't have to think geometrically. It just comes right out of the question using Lagrange multipliers. And it discovers another symmetry for us that we might not have noticed. Right? A symmetry in y equals negative x. Okay, so now we've got those terms there. If we plug those guys in here, x equals y, we wind up getting the following critical points. Okay, so these are the two critical points that we found from y equals x before. And this time we get extra critical points, or new ones, I guess. One over root 2, negative 1 over root 2, and negative root 2, 1 over root 2. Okay, so those are 4 critical points that we get by solving this. Okay, so let's finish up by drawing what these are. Okay, so there's our unit circle again. Right, and now we've got 4 points. We've got these two, which correspond to our maxima, this one, which corresponds to a minimum, and this one, which corresponds to a minimum. Okay, so the green guys are mins, and the blue guys are maxes. So what did we do? We set up the Lagrange function, we found the critical points, we got 4 points, and then we figured out which ones were mins and which ones were maxes. Okay, and those are exactly the points where those level curves are going to be tangent to our function. Like that. Okay? Questions there or thoughts there? Okay, so I propose that we take, what time is it now? Let's take a 7-minute break until 10:10. If you've got any questions, you're welcome to come up and ask, okay? All right, so for the second half, I want to use Lagrange multipliers a lot. As I was saying, when you're solving these constraints, the algebra gets a little bit gets tricky. So I want to draw your attention to the algebra and also give a nice kind of geometric fact related to Lagrange multipliers. So let's do another example of optimizing with Lagrange. Okay, so we're going to do a maximization. Or let's see, is it a max or a min? Max. Okay, so I want to maximize ln x, ln y, ln z, subject to x plus y plus z is 1. Okay, this function ln okay, so I could talk about this thing all day because it's very exciting, but this sum of logarithms on this thing is often interpreted as a function on the set of probabilities. Okay, we often think of x plus y plus z equals 1 as a set of probabilities. And this function that I've written down has very nice properties. But if you want to talk about probability, we'll do that another time. Let's just maximize this thing for the time being. Okay, so what do we got to do? We got to set up the Lagrange function. Or sorry, first off, our constraint's given to us this way. We have to rewrite our constraint. Right? The reason for rewriting the constraint is so that it becomes a natural part of our critical point calculation. Okay, good. Now we'll set up our Lagrange function. Lagrange, by the way, really neat guy. Worked in pure math, also worked in physics and celestial mechanics and stuff.
And despite the name, he did marry.
Right, yeah. Worked in Italy. Very French-sounding name, though. Okay, so there's our Lagrange function. And now what do? We find the critical points. Okay, critical points. So we're taking derivatives of ln. So the derivative here will be 1 over x minus lambda is 0. Okay, and then we get here. Okay, so we have to think a little bit about the algebra of what's going on, how this could possibly work out. Right, how can we solve for x, y, and z and stuff? So a move that's often helpful with Lagrange multipliers is to isolate for lambda. Okay, often you can get all of these things to equal out to lambda. Okay, and that gives you relationships among your variables that you didn't have before, right? It gives you relationships among x and y, among x and z. So these tell us that these guys all equal. So that's very helpful, especially if we rewrite it like this, that they all equal each other in this way. And now we can go down here and solve. These all equal each other, so they all equal x. And obtain that they're all equal to a third. Okay, so we've got a critical point, but now we don't have a good way to determine if it's a max or a min. Right? We've got one critical point. There's no other values to compare it to. Can anyone argue for me that this should be a max and not a min? Requires a bit of out-of-the-box thinking. Okay, one second. Right? Well, how small can we make this value, I guess? Subject to this constraint, right? X plus y plus z, how small can we make the total thing? Maybe run an argument by your neighbor. Give it a shot for just a moment and see if you can argue that this can be made very small. E to the negative 1,000. Yeah. Right. Okay. Cool. All right. Okay. So let's bring it back. So any suggestions now on why we can make this very small? Yeah, any thoughts there? Did anyone come up with an argument where they're like, yes? Or did anyone come up with an argument where they're like, maybe? Anyone over here? Over here, maybe? This guy, you've got an argument.
Yeah, again, so we were just saying you can make the function f x, y, z arbitrarily small as possible. So choose any negative number.
Yeah.
Take x to be as close to 1 as you like. And then choose y or z small enough. So for example, x 0.98.
Yeah, you can make this guy negative by picking x and z close to 0, right? So yeah, so like y is 0.01 or something, right? That would give you a small value. Or you could take z is e to the negative 1,000, right? Then your functional output negative 1,000. Right, so good. So we can make this guy as negative as we want. So the value we've obtained should be a max, right? It's definitely not the minimum of the function. And so it should be the maximum of the function. Okay, that's often a helpful heuristic for understanding these things. Okay. Okay, so now I want to do an example which says something about the geometry of Lagrange multipliers that sort of suggests something geometrically useful that we can get. Okay, so this is question 30 from section 3.4. Okay, so suppose we've got a subset of R3, which is a surface defined as the level set of a function. And suppose that we take a point on S. Suppose P is the point on S, or let's say suppose it is a point on S. So that the distance of that point back to the origin is maximal. Okay, and our claim about this guy is that the vector from the origin to P has to be perpendicular to S. Okay, so when we were back earlier in the beginning of the course, we were talking about, the the closest point on a plane, right? So we've got the plane, we look at the closest point to the origin, and we said that's perpendicular. This is the same kind of thing. Now we've got a surface, and we're saying if there is a point of maximal distance, then it has to be perpendicular to. Okay, so let's set up this question as a Lagrange multiplier type thing. Okay, so what's the constraint here? What's the constraint that we want to use? Okay, what's the function we want to optimize? We've lost them. Okay. Right, so here's a function we have to satisfy, and then we've got this distance involved. Okay, so I want to use that distance and that function. So the goal is to consider maximizing this on this surface here. Right, so that's our the function we're optimizing, and there's our constraint. So the Lagrange function will be that distance minus lambda f minus 1. Oh, sorry, we need a lambda here. Okay, so there's our Lagrange function. Now, if we're a critical point of this Lagrange function, what do we get? Then we get this guy here. Okay. Oh, sorry, that should be a Z. Okay, so let's spell out what this means in terms of coordinates. Okay, so thinking in terms of coordinates, we can just calculate the derivative d sub x, right? So in terms of coordinates, right? We take the derivative of distance and we get this guy. And we're saying that's lambda f. Lambda fy. Okay, so now I want to observe the following fact. This guy here, x, y, z, that's parallel to our original vector. Right? So this is really some number times x, some number times y, some number times z. Okay? Okay, so what's that telling us about the relationship between the gradient and the vector pointing to this point? Right, so we've got the vector x, y, z, and then we've got the gradient at that same point. So we obtain k times that vector is, oops, the gradient of f. And we know that the gradient has to be perpendicular to the surface. Okay, so looking along the vector from the origin, we get something that's parallel to the gradient. The gradient is perpendicular to S, so the line is. Questions about any of the reasoning there or the thoughts there? Yes?
For kx equals, is that 2x or dx? Derivative or 2x?
Yeah, these are 2's. And I didn't cancel them just so that they kind of look consistent or something. Yeah. Yep.
If we have maximized for distance squared instead?
Yeah. If you're a maximum of distance squared, then you're a maximum of distance. And oftentimes, I mean, we're lazy, so we want to save writing, right? So if we maximize for distance squared, then we don't get those square roots. Yeah, good. Okay, so sweet. So that sort of gives us kind of a nice geometric fact coming from the method of Lagrange multipliers. Okay, and this key idea about gradients. Okay. Okay, now I want to do one more example of the kind of algebra that comes up when we're doing Lagrange multipliers. it's one of these things, every time I teach this course, I go, oh, I want to do that example. And then I struggle with it for a half hour because the algebra is tricky. So let's go through the algebra together. Okay, so this is one of these sort of manufacturing questions. Okay. Suppose you make boxes. Why do you make boxes? Beats me. Okay, so the boxes we make okay, the top and bottom of them are made out of one material. The sides cost $3 per meter cubed. So we want the least expensive box with volume 1 meter cubed. When you're setting up these physical optimization questions, I find it very helpful to imagine what kinds of shapes could arise. Okay, so if we made, you know, a big thin box like this, that box would have a lot of surface area on the sides. Okay, so that box would be very expensive. If we made, you know, we wanted to minimize the amount of surface area on the sides, then we'd have a huge top. Yep. Oh, sorry, squared. Derp. Yep. Perfect. Meter cubed there. Yeah. Sweet. Sweet. So here we'd have, you know, a lot of surface area on the top, and that might wind up being inefficient as well. So we want to figure out the optimal balance between top surface area and sides surface area. Okay, that's our goal with the optimization. Okay, so let's draw a picture and label the variables. Right. Oh, and I guess there's sort of a step when you're doing these physical things. Okay, imagine the possibilities of how this could play out. Okay, so we'll draw our picture with variables. Right, our box has 3 dimensions. Let's call them x, y, and z. Okay, now let's state our goal. Okay, so we want to maximize, or we want to minimize cost. So we want to minimize this cost function. And we'll figure out what that is. Subject to this volume constraint. Right? Subject to the constraint that the volume is equal to 1. So that volume will be x, y, z. And we have to spell out the details of our cost function now. So this top and bottom cost one amount. And then the sides cost some different amount. So the top and bottom, that will be $2 times 2xy. Right? We've got the top here. It's got dimensions xy. And then the bottom also has dimensions xy. Okay, so there's two guys there. And then we've got $3 times 2xz plus $3 2yz. Right? So the xz term is for this face. The yz term is for this face. But there's another one on the other side of the box. Okay. Is everyone okay on that cost function? Yeah? Okay. So there's our cost function. Okay, so we set up the Lagrange. Okay, so our cost is over here. 4 Okay, there's the cost minus this guy. Okay, now we find our critical points. Six Z oh wait, that's the y, so that should be y is xz. Okay, very good. So there's our conditions on the critical points. Key observation about these guys, again, these are nonlinear conditions. Okay, they're not linear in x, y, and z because we've got these products over here that make things really tricky. The move that I want to highlight for dealing with this is you know something about the product x, y, z. Right? So what we're going to do is we're going to use that fact. So this is sort of like key tricky move. Okay, is to multiply in an x here. So multiply this whole equation by an x so that you get rid of that nonlinear term. Okay? You introduce things over here, but now you'll be able to isolate for lambda, which is a key tool. So this will give you 4xy, 6xz, minus lambda times 1 is 0. So we multiply in an x onto all three terms. X, y, z is 1, so we write it as 1. Here we multiply in a y. And here we complete this by multiplying in a z. Okay, and now we've got all these things that equal to lambda. Okay, so we get right. Oh, some algebra went wonky here. This should be y times z. Yeah, thoughts, questions there? Okay, so here we've got something equal to lambda. We can set that equal to our next line. Okay, so this is a very helpful move isolating for the lambdas, because now it gives us relationships among our variables. These guys cancel, and we get uh, 6xy is 6yz. Okay, so there's two ways this could go. Oh, sorry, 6x. There's two ways this could go. Either z is 0, or these two guys are equal. Okay. If z winds up being 0, we can't possibly have any volume, right? So that's off the table. Okay, so we get x is equal to y. Okay. So we've got this, which is good. And now we need one more relation. So we'll use these two guys in relationship to each other. Okay. These guys cancel. All right, now we have the following. So this tells us either y is 0 or 6xz. Oh, yes. Thank you, thank you, thank you, thank you. Right, so either x is 0. This is the part of lecture where the dyslexia really shows. Right, so either these guys cancel, or y is 2/3 z. Sorry, y is 3/2 z. So this one, we would have no volume, and now we've got our constraints on what happens. Okay, so that totally constrains where the optimum can be. Let's pencil out the last couple details. Okay, so we get something like this as our final dimensions on our box. Okay, again, we can use this heuristic about maxes and mins, right? We've got these constraints, but how do we know that this is a minimum? Well, we could always make a more expensive box. Right? We could make this thing as expensive as we want. So the thing that we have should probably be a min. Okay, very good. So I guess the exercise here is to solve for these guys. Okay, using this volume constraint. Okay, so just to wrap up, I'd like to go through and summarize what we did this week. Okay. So what did we get up to this week on Tuesday? What were we up to on Tuesday night? Yeah? Yeah, so that's been the theme, yeah, is constrained optimization. Okay, did we develop any theory on Tuesday night? Did we have any new tools? Yeah? Yeah, right, this endpoint checking stuff. Right, so when we've got a function in one variable we check the endpoints. And in this course, often we have two variables, so we check the boundary. Okay, yeah, very good. All right, did we have any methods? Oh, right. We introduced all those new terms about extreme value. What were those terms, and what's the extreme value theorem? Yeah? Yeah, so we've got bounded sets. We've got closed sets. Right? Previously, earlier in the course, we had met open sets. Okay, bounded, closed. All right, we had the extreme value theorem, which is extremely valuable. Okay, we had the extreme value theorem. Okay, and then what did we get up to today? What was the major theme today? They've already lost it. Oh no. Okay, right, so major theme of today, Lagrange multipliers and parallel gradients. So let's put that. Oh, there's one other thing I want to put because it is relevant for the homework. This is the find max min using level curves. Okay, where we just plot the level curves and find the last one that meets the set. Brief reminder, if you want to pick up your remarked test, that's this Friday, 4 till 6 4 till 6 in IC 200. So tomorrow, IC 200 from 4 till 6. Okay, thanks a lot, folks.